Dr. Thomas Ludwig is the John Dirk Workman Emeritus Professor of Psychology at Hope College. He joined the faculty there here in 1977. And over the next 40 years, he has taught courses in developmental psychology, adult development and aging, psychology and religion, and neuroscience. He's also served as adjunct faculty member at Western Theological Seminary, teaching a course on ministry with aging. He has served as Hope's faculty exchange professor at a university in Tokyo I can't pronounce. And he has been interim professor of Trinity Lutheran Seminary in Columbus, Ohio. He received his BH from Concordia College, MA from Christ Seminary Seminex, and PhD from Washington University in St. Louis. Please greet Dr. Thomas Ludwig.
Thank you. I am so glad you came back for the second week. I wondered whether the subject matter would discourage some of you. But remember, I warned you, have an extra cup of coffee for today because we're going to dig a little deeper than last time. Before we get started, I want to remind you that last week the HASP coordinators sent out a link to a resource page, which I prepared. If any of you get really excited about this and want to follow up on some of these ideas, this would be a good place to start. And last night, because last week there was considerable interest in the idea of self-driving cars and these humanoid robots that are appearing, I've prepared a set of links that would provide some access to that kind of information. But you folks at home, don't try this right away because I can't access this server from home. And so now that I'm on campus after this session, I'm going to upload the revised page with these links about robots and self-driving cars. And then also I want to call your attention to two important articles published in the New York Times. I referred to one of them last week. It was published on March 14. And there was another one that came out yesterday about the importance of China and the United States working together on AGI, especially guardrails for AGI. And so I'm going to be talking about that next week. If you want to read some of that in advance, please go ahead. Okay, so as I mentioned last week, when I think about what everybody should know, by everybody, I mean educated people who are really interested in the future of our society, what everybody ought to know, they ought to know some history. What is artificial intelligence? How do we get to this point in the development of artificial intelligence? Secondly, I think they need to know what makes the current crop of artificial intelligence models so much better than the ones that came before. So that's what we're going to focus on today. And then next week, and I'll be talking all the time today as fast as I can. But next week, I'm going to build in a lot of time for discussion. And so this is your chance to talk about what you think are the implications of this new form of AI on your own lives and on the lives of your children and grandchildren, on society in general, as it relates to art, culture, ethics, religion, the idea of what it means to be a person. All of those things we'll touch on next week. Okay, this session is going to pick up where we left off in the first session with the history, and then talk about what makes today's generative AI so powerful, so unique. So to kind of set this off, I asked DALL-E to create some images of what it thinks, okay, would be the concept of generative artificial intelligence. And I did this first a year ago, and the two images on the left represent what DALL-E came up with. And you notice that both of them have brains in them, or a representation of a brain. So I did it a couple days ago and got the image on the right, which you noticed no longer has a human brain in it. And I actually like it a lot, because when we're talking about generative artificial intelligence, we're referencing the human brain, but there's nothing brain-like about what actually is coming out, right? This is the product of mathematics. This is the result of many complex mathematical equations being put to use. Okay, so with that background, let's quickly recap what we covered last week. I gave you my favorite definition of artificial intelligence from IBM. It goes like this. Artificial intelligence leverages computers and machines to mimic the problem-solving and decision-making capabilities of the human mind. And I pointed out that every definition that you'll come across about artificial intelligence defines artificial intelligence in relationship to human intelligence. So what is human intelligence then? What makes you an intelligent being? Well, cognitive psychologists would argue it's your flexibility, your adaptability. You can adapt to your environment. That's what makes you intelligent. So when you come to a new situation, you can assess that situation, you can analyze it, and then you can devise strategies that compare your performance in the past, how you approach similar situations, whether it worked, whether your strategy worked or not. You can devise a strategy that you think would be effective in the current situation, and then you can revise that strategy as you go along on the fly in response to whether your strategy is working or not, right? So kind of the definition of a non-intelligent person would be somebody that keeps using the same strategy even when it no longer works, right? And that would not be adapting effectively to the new situation. Now, the early successes in AI, and there were many, starting in the late 1940s, stretching through to at least 2000, and some people would say all the way up to 2015 was the kind of old era of artificial intelligence. When we look back now from the privileged position of our current history, we can see that the successes mainly occurred when the power of AI was directed at small problems. By that, I mean focused problems, things that had moderate complexity and could be easily defined by how a human would approach it in that situation. But then the attempts at creating a computer system that simulated or mimicked the full range of human intelligence failed dismally. And it failed, those attempts failed for a couple of different reasons. One of them, and I'll keep hitting this, had to do with hardware. The computing hardware was not powerful enough. It could not do enough computations per second, and it especially didn't have enough memory to keep all of this stuff in storage that it needed to process at the same time. But it also failed, attempts at artificial general intelligence failed because of the software. The algorithms that were in use were not sufficiently powerful to actually use all the capacity of the hardware anyway. And it made it too difficult for programmers to give the proper instructions to the computers in order to get the output that they wanted. So we have two developments occurring simultaneously. We have improved hardware year by year, decade by decade, and we have better software algorithms for sucking out the greatest power out of that hardware. Okay, now the past attempts at artificial general intelligence failed dismally. But now we're getting, in this new era, we're getting closer and closer. It's kind of discouraging because the tech leaders always say it's just 2 or 3 more years out. You know, they say that it said that in 2018, and they're still saying it now. It's always like 2 or 3 years out, but it is coming. I mean, we will get to the point. I mean, the projections, people who are paying serious attention to this are really worried that we're going to get there before we have the means to control it, to the means to keep bad actors from using it in very terrible ways. But anyway, that's for next week. Okay, so what we're focusing on this week is how is it that these new AI systems have kind of leapfrogged over all of the problems that we had in the past? How did they get to be so powerful that we're now starting to pay attention? Even ordinary citizens. It's not just the military planners and the computer scientists who are following this. Now, lots of people in the general public are aware of what's coming and how powerful these systems are and how they're going to be. So to go back over this again, the past successes we might call in the area of artificial narrow intelligence. That's, like expert systems. Whereas artificial general intelligence is this elusive dream out there of the super intelligent AI. Now, the expert systems I talked about last week, guided missiles, chess-playing computers, recognizing license plates, and the beginnings of self-driving cars. We're not quite there yet, but even then, probably in your lifetime, you're going to be riding in a car that has no steering wheel. Because those cars, humans will not be, if a full level 5 autonomous vehicle is never intended to be driven by a human. Humans can't drive them, and that's coming, but nobody's there yet. Okay, the other thing that's changed is the way we interact with computers. And starting from back in Alan Turing's day, where you had to flip switches on the computer to send the programming instructions to the computer, very slow, laborious process, to punch tape and then punch cards, and then teletype machines that you could type on and print out things, to now you can talk into your phone and give it all the instructions you need. Well, I'm going to tell you a little bit about my own personal experience with AI. Back in 1981, I made an attempt to develop a text-to-speech and speech recognition system, and I'll talk about that. And also, you now know that it's possible to talk to your computer and have your computer answer you in a somewhat intelligent conversation back and forth. Back in 1985, I made my own attempt at this version of AI, and I'm going to talk about that in terms of the limitations of the early forms of AI and how modern AI is different. Okay, now, if we step back and look at the big picture, I believe that the history of AI reflects a kind of dualism. That's a philosophical term. That there are two kinds of things. There are minds and bodies. There are material things and non-material spiritual things. That's dualism. Anyway, the scientists who've been working on AI wouldn't describe it this way. This is my own interpretation, but it might be helpful if you follow along with my thinking here. The history of AI reflects a kind of dualism that separates the physical brain from the non-physical mind, the mental capabilities of a person versus the brain that carries out those abilities. Now, from my perspective, the early AI programs were built around a model that simulated a human mind. That is, they were built to give instructions to the computer that would follow the logical organization of the way that a human would solve a particular problem. That is, they were focused on the mind end of this thing. That worked really well for simple projects like math problems, right? We can describe in English how to solve certain math problems. And if you go all the way back to Lady Lovelace, right? Anything that you can describe, you can tell if you can tell the computer to do it, the computer can do it. Now, the other important thing about this is because humans already understand how to do these problems logically, when the computer does it, we know why, we know how it's working. We understand the way that the computer is working because it works the way that a human mind would tackle that problem. But recent progress, in my opinion, has been because we adopted a different approach. Instead of trying to emulate the human mind, we started to try to emulate the human brain. Now, this works really well for much more complex tasks like facial recognition. First of all, try to program a computer step by step to recognize faces. It first requires that we understand how humans recognize faces, and we still don't know how they do it. I mean, the brain is so complex. We have some hints, we have some ideas about how the brain does it, but we really don't know how the brain does it. And so how can you program a computer to do something that we don't know how humans do that same task? But if you then try to get the computer to emulate the human brain, now we've got a chance of mimic what the brain is doing. Even if we don't understand what the brain is doing, we're mimicking what the brain is doing. Lo and behold, we made progress in recognizing faces. So um, my kind of shorthand way of talking about this is the old way from 1947 to at least 2000, maybe beyond that, was doing AI the hard way. And that's a pun deliberately, because not only is it more difficult, but it relies on what we call hard coding. That is the the intelligence is hard coded into the program. And once the computer starts running, we can't change it. The computer has no control of it. It's simply following the logical steps that the programmer hard coded into it. So that's emulating the mind, right? It's trying to understand how an intelligent person would solve this task. And now we program the computer to follow the same logical steps. So the programmers write the code that teaches the computer how to do this. The computer runs the code, and lo and behold, the computer appears to be intelligent. It's engaged in intelligent behavior. It appears to have artificial intelligence. Now, we can go all the way back to 1947. I told you about Alan Turing. I hope you knew about him before I described his work last session. But after World War II, after his tremendous success at breaking these Nazi codes, the British government put him in charge of the most powerful digital computer, building and maintaining the most powerful digital computer in the UK. I was at the University of Manchester, and from about 1947 to 1949, Turing was part of a team that managed this and developed it. And one of the jobs that he did was to write the program interpreter, that is to write the program that allowed other people to write programs to control the computer. So in modern terminology, maybe some of you have done some computer programmers. You might know Fortran or BASIC or COBOL or one of those other languages. That is a language that allows other people to use programming logic to control a computer. But you can't just type the Fortran or BASIC commands. It has to have something that can interpret that and translate it into language that the computer can understand. Got that? Okay, so Alan Turing wrote the first program that allowed other people to write programs. And Alan Turing's very first program was to do a long division problem. So he actually taught a computer to do long division the way that humans would do long division. We understand how people do it step by step. You were taught in fourth grade, you were taught a sequence of steps. You can program those sequence of steps, and it worked. Okay, so the problem here is it only works for problems where we have a logical sequence of steps, where we understand how people would solve the problem. It's also very time consuming because you have to tell the computer every little detail of what you want it to do. And then if we change the situation even slightly, the algorithm fails because you need to go back in. The programmer needs to rewrite it for the instructions that would be needed for the new situation. Now, as an example of this hard coding method, I'm going to tell you a little bit about a project I did. I came to Hope in 1977. In 1978, the government bought me my first laboratory computer. National Institutes of Mental Health gave me a grant, and I was working on a project that involved transferring information from the left hemisphere to the right hemisphere and from the right hemisphere to the left hemisphere of the brain. That was my research back in the 70s and 80s. And so what I needed was a device that could reliably present simple words to the left ear or to the right ear under specific time constraints. And the tape recorders of the day could not do this because there was always some lag in starting up or stopping, whatever. So I built my own device. And believe it or not, I still have, this is from 1981, I still have the output part of this. I lost the rest of the mechanism. Basically, what this did was it allowed me to type on a computer. And by the way, This will mean something to a few of you in the room, probably. By 1981, I had two Z80 computers. And this was before IBM PCs, right? There were no IBM PCs until 1982. And so back in 1981, these were the most powerful microcomputers that that the general public could purchase. I had two of them in my lab, and they were wired up to specialized audio synthesizer chips. Some of them are still, those chips are still in this little box. And what the computer could do, what you could write a program that would specify the speech waveform. And so, for example, if and by the 60s, we had a very good idea of what the speech waveform looks like. So when you say the syllable ba, we can plot exactly how the pitch and loudness of what's coming out of your mouth changes millisecond by millisecond. And once you have that, then you can program a computer to drive a audio synthesizer chip to recreate or mimic that exact pattern of sound. And so my device could go ba, okay? And now if you combine ba or ba with ah with t as individual sounds, phonemes in the English language, you get the word bat, right? So I could have my computer play through a stereo headphone set that I could play bat to one ear at the same time that I was playing another word to the right ear. And it worked perfectly, but it was extremely time consuming. And fortunately, we don't have graduate students at Hope College. We have a lot of very bright undergraduates, and I had a couple of them working in my lab that were willing to dig into this and learn the programming for these Z80 computers so that they could assist me. And we eventually came up with a set of consonant, vowel, consonant words that were adequate for the research that we were doing. But if we tried to add additional words, let's say we're going to change the experiment a little bit, and now we want rhyming words or something like that, we have to do all that programming over again, step by step, hours and hours and hours. And so what I learned from this is, number one, 1980, 1981, the computers were not really powerful enough to do this. And secondly, the software limitations of doing everything step by step by hand, not good enough. And so within a few years, the software got better. If I would have stayed in doing this kind of research, it would have become easier and easier. But you get the point? Here was my first attempt. It worked, but it was hard. It was doing it the hard way. Now, in 1985, I did my second venture into AI with communication between people and computers. I built an interactive chat bot. I called this chatbot Computer Therapist. And what I was trying to do was teach students a little bit about Rogerian therapy. Some of you are familiar with that technique of client-centered therapy or non-directed therapy. It was based on ELIZA. I talked about that last week. And everything, just as in ELIZA, everything was hard-coded. In my project, everything was hard-coded. But my project focused on the environment of a college student. And so I came up with a list of 80 keywords that my program was going to watch for when the student typed any of those words in. Then I had 3 appropriate responses, canned responses, that the computer would display to the student, and it would rotate at random through those. So if they said the same word twice, they wouldn't get the same response. And then I also programmed in 10 generic responses in case my program couldn't recognize anything important in the student's response. Okay, so this was a pattern matching project. When the student typed in a statement, my computer went laboriously step by step through the sentence, analyzing each word one at a time, trying to match it against any of my keywords. And if it did, then it generated the appropriate response to that keyword. If there was no match, it tried to reflect the statement back to the student in the hopes of prompting the student to say more. Okay, So before I show you a quick example of a dialogue or conversation between a student and my chatbot, I need to say something a little bit more about the reflect rule. What does it mean to reflect back a statement? And so basically, if the statement contains I am or I'm, the rule would be take off the I am or I'm, but keep the predicate. And then replace the I'm with how long have you been, whatever. So here's an example. If the student types, I'm feeling pretty discouraged, you get rid of the I'm, but you keep the feeling pretty discouraged, and you replace it with how long have you been feeling pretty discouraged. Got that? Okay, so let's go through a quick example. The computer therapist says, welcome. What's on your mind? Student says, I'm feeling pretty discouraged. Okay, I should have had discouraged in the list of keywords, but um, I didn't. And so the computer simply had to reflect that back. How long have you been feeling pretty discouraged? Okay. It's been a while. And so there's no keyword in it's been a while. And so now all the computer can do is give a kind of generic response like, I see, tell me more. If any of you have been in non-directive therapy counseling, this should sound pretty familiar, right? Okay. And so then the student says, the student takes the bait and says, I'm worried about my grades. Grades. Okay, that's a keyword. And so then one of my canned responses comes out. Yes, that's a common concern for students. Is your academic performance important to you? By now, the student's beginning to think, maybe this computer understands what I'm saying, right? Because this response seems appropriate to what's on my mind. And the student says, very important, even more important to my parents. Whoa, okay. Parents, I had the forethought to put parents in as a keyword. And so, your parents. How do you think they feel about what's happening? Now, notice this sentence has no connection to what the student has just typed, but the student thinks it does because we've been talking about my grades. And so this what's happening kind of applies to the generic situation of, your academic performance and so on. And so the student says they're definitely upset with me right now. I should have had upset in there as well, but I didn't. So it has to reflect why are they definitely upset with you right now? And the student says, I guess I'm a disappointment to them. And I don't know why I didn't have discouraged in there because I did have disappointment in the list. Can you say more about the nature of this disappointment? And by now the student's getting kind of tired and it's also kind of pulling back, wondering if this is being recorded. Is the computer going to send this to his parents and so on? Not really. A generic response is, let's move on. Is anything else bothering you? And the student has had enough. No, I think I'm getting bored with this conversation. I did have the keyword bored. I was anticipating that after a few minutes, students would have enough of this. And so the therapist says, what do you typically do when you're bored? Trying to get the student to hang on a little bit longer and stay engaged in the conversation. But the student is done. He says, I'm out of here. And I have the keyword goodbye in there. And so the computer therapist says goodbye. And I hope our time was helpful and all this sort of stuff. Okay. Any questions about that specifically? You see how this all worked? Okay. So now it's your turn. So I'm going to give you a minute and a half again to turn to the people around you, close to you, and talk about in what ways do you think that my attempt at interactive communication between a human and a computer reflected intelligent behavior on the part of the computer? And then whatever you say about that, what do you think in 1985 was still missing? Okay, minute and a half. Those of you at home, think about these if you want to jot something down or if you want to post a comment, this is the time to do it. Okay, it's time to wind this down, finish up your little conversations. And for this one, I'd like to hear what a few of you said. So would any of you want to report what your little group came up? Can we get the microphone here, please?
We thought that there was a bit of intelligent behavior there because the chatbot understood the language.
Okay.
But what it didn't understand is the emphasis on each word. For example, how do you say things? How do you say things?
Yes.
How do you say things? How do you say things?
Yeah. And so just another note about that, part of communication is words, but part of communication is the tone of voice and the facial expressions and gestures and so on. And of course, all of that is stripped away. We're just looking at the words. Anybody else want to report what your group here? We've got somebody up here.
The four of us here concluded that it was not intelligent behavior. It was just canned responses.
Right.
And number two, it had no aspect of human intelligence because it doesn't contain any knowledge of empathy or so I guess we decided it was a total failure.
Okay. Remember, this was 1985, and this was state of the art for what you could do back then. But so I would say that there is a tiny bit of intelligence in there, but it's the intelligence of responding to the environment, to the situation. So the computer therapist was not just saying something at random. The computer therapist was in some way reacting to the situation. That's slightly intelligent behavior, but and some of the students actually, for at least a little while, got caught up in the illusion of this, and they felt like they were actually being understood. But the program did not understand anything, right? It was simply looking for a word and treating all words in the sentence as of equal value. That's something that since 2017, computers have been able to pay more attention to the important words in a sentence than the non-important words. And I'll say a little bit more about that later. Okay. I'd like to move on now because I still have a lot of hard stuff to say before we get going here. So up to a point, more money bought better performance. And so, you know, Hope College had limited resources. I had a limited amount of time and programming skill and talent from students to be able to put into this project. But other individuals and companies who had lots of money and lots of time to spend on this made progress during the 70s and 80s, throwing more money at this hard coding approach. And they actually got pretty good. So do you remember when zip codes came in? 1963. As soon as zip codes were introduced, the U.S. Post Office started throwing millions of dollars at a system to try to be able to automate the reading of typed zip codes. And so throughout the 60s and 70s, by the mid 70s, their systems were pretty good. They got up to like 90% accuracy for reading a typed zip code, but they still couldn't do handwritten zip codes. All the handwritten, hand addressed envelopes had to be sorted by hand by human eyes, looking at that zip code and figuring out where it should go. But in 1997, the post office introduced a system. Finally, the AI was good enough that it could read handwritten zip codes at 40% accuracy. 40%. So that meant 60% of the letters got kicked out, and some human had to look at that and figure out what the zip code. And until 2013, there were 55 hidden postal locations throughout the United States with thousands of employees who did nothing all day but look at images of poorly addressed letters and try to figure out what address this letter was supposed to go to. All those systems have closed down. Now, there are still a few letters that can't be identified, but they're a small enough number. They're up to 99 point something in terms of being able to recognize the handwritten address on an envelope. So, but back in the 60s and 70s, this was all hard-coded for every possible font that a typewriter or then computer printers could type the zip code in. And Bell Labs, the phone company, right, invested millions of dollars in the system that could speak the digits 0 through 9. It took them much longer to develop a system that could recognize what you said when you called in. But eventually they got to automated voice systems that worked both ways. Now, all of these systems were focused on a narrow problem, and gradually they got better and better as the hardware and software improved, but they still didn't approach what an average human could do easily, right? They did not approach artificial general intelligence. And so this takes us back one more time to Lady Lovelace's objection. These computers were not, quote, intelligent. They couldn't think. These systems could do anything that we knew how to tell them to perform, but they didn't originate anything. They couldn't learn on their own. They couldn't go beyond the intelligence that the programmer had programmed into it. Does that make sense to everybody? You're with me on that? Okay, so now to one of the heroes in this situation, in this history, from my perspective. You know that I think of Ada Lovelace as one of the heroes, and Alan Turing, Donald Mackay, and Geoffrey Hinton, who won the Nobel Prize just a year ago for his work in artificial intelligence. Anyway, way back in the mid 80s, Geoff Hinton said, if you want to make a device do something intelligent, you've got two options. You can program it, that's the hard way, or it can learn. And that's what we're going to be talking about now. Now, so my view is, I've said this before, but let me drive it home. I think that the remarkable progress in the last 15 years, especially since 2017, is the result of a remarkable shift in perspective. And I think Geoff Hinton is one of the people that deserves credit for this. From an approach of programming the strategies to do a task, that's the hard way, to programming the strategies for learning how to do the task on its own. How, if we can get the computer system, if we can program the computer system with the intelligence to learn how to do something new, then we don't have to do all that programming by hand. A human doesn't have to do that programming because the computer now is starting to learn on its own. Now, there's the hidden part of this equation is all during these years, computer hardware was getting more powerful, and the computer programming systems were also getting more powerful, and that's what made this shift possible. If Geoff Hinton had come up with this idea in 1962, it wouldn't have worked because the hardware and software could not have supported it. But in order to understand what Geoff Hinton's breakthrough was in the mid-80s, we need to go back to cognitive psychology. How is it that humans learn? Now, remember, at all of these AI teams across the country and around the world were composed of computer engineers and computer scientists on the one hand, and they always had cognitive scientists, cognitive psychologists on the team as well, because the cognitive scientist's job was to identify the steps in how a human would solve this problem, and then the engineers and programmers then tried to make the computer emulate that. Okay, so all of these cognitive scientists on the team had been influenced by a Swiss psychologist called Jean Piaget, who proposed a theory for how intelligence grows in humans. He believed that that intelligence, what your intelligence consists of, is a combination of the structure of information. You have the raw materials, the building blocks for what you know, and Piaget believed that that information was contained in what we might call pigeonholes called schemas. And a schema holds the information that you need to be able to solve a problem. Now, that schema is kind of slippery concept because it could be a concept, it could be an idea, or it could be an action pattern, a pattern, a strategy for moving your arms around in space to do something. I'll give you an example of that. In addition to the structure, primarily these schemas, your intelligence also consists of functions that can do things, adapting to the environment. And according to Piaget, the most important functions were assimilation and accommodation. Assimilating means using your existing schemas as is without changing them. Or another way of thinking about that is when you hit a new situation, you incorporate that new situation into your existing schema without changing the schema. That's assimilation. On the other hand, accommodation means altering your schema, modifying your schema in response to the new situation, or even creating a new one. If your old schemas just wouldn't work, you need to go start from scratch and build a new one. Okay, so the example I'm going to use is a 5-month-old infant developing a reach and grasp schema. So that's an organized, coordinated pattern of behavior. 4-month-old infants don't have it. Sometime between the end of the 4th month, the 5th month, 6th month, this develops in all normal infants. And so by 6 months, most infants, you show them something, a rattle, hold out in front of them, they can reach out and grasp that. They have that coordinated pattern of behavior, which is really complex when you think about all the muscle movements that need to be coordinated in order to reach out and grasp something. Now, our job is to try to teach a computer how to do this. And so in order to teach a computer to do it, we first have to understand how it is that a child does this. And so I've turned the child around so we can see this better. The child's looking at the star, and we can describe the initial position of the child's right hand circled in red using a formula, right? We can say that position P represents a function of the child's hand in a 3-dimensional space, where we're going to say that there is a numerical value on the x-axis that represents the horizontal position of the child's hand, and a numerical value on the y-axis that represents the vertical position of the child's hand, and a numerical value on the z-axis that represents how far the hand is away from the body. With me so far? Okay, so now, here's where the P is the initial position. It's down by the child's right hip. And the T is the position of the star. So the child has to somehow get the hand to that star. Okay, you tell me what's going to happen. So what's going to happen to the y-axis value? It's going to increase in a positive way, okay? So if we think about this, the child's practicing moving the arm around trying to reach and gradually gets better and better. The child learns that if the star is in that position, the child has to raise the hand. That's positive on a positive offset to the y value. What's going to happen to the x value? It's going to be negative. We have to add a negative value to shift it more to the midline. And then what's going to happen to the z value? Positive value as we shift it out like that. Okay, the child does this again and again and again. The child then gradually acquires this complicated schema, reach and grasp schema. First, if the child is trying to grasp the star and it's in the same position, the child's assimilating. Once the child has that schema, the child can it's got this practice behavior, can reach out and grasp the star. Now we fool the child, we move the star. Now the assimilation of, the existing schema won't work. So now the child needs to accommodate. The child needs to adjust or modify the schema to be able to get the hand to the new target position. Everybody with me so far on this? Okay. Now, this is math, right? We can build a math model to describe the movement of the child's hand in this three-dimensional space. So now I'm going to introduce the terminology here. This function that's going to give us the new target position has the numerical value on the x-axis, the y-axis, and the z-axis in there. But to each of those, we are adding another numerical value, which we're going to call the offset. And that as the child adjusts each of those offsets, the child gradually gets better and better at reaching this new target location. In Piaget's terminology, the child is smarter than he or she was before. Intelligence has grown through this interplay between assimilation and accommodation. That's what we mean by saying the child has gotten smarter. The child has developed a reach and grasp schema and can adjust that reach and grasp schema in response to a new situation. Now, I want you to turn back to the other people in your group for another minute and a half. And this time, I'm not going to ask for feedback. I just want you to talk about it. I want you to talk about these two issues. Imagine that you already knew everything about artificial intelligence, and now you're listening to me talk about it. What's happening in your brain while you are listening to information that you already know perfectly? Then, all of a sudden, I switch to talking about the physics of quantum mechanics, and you know nothing about it. What would be happening to your brain as you're listening to that? Okay, turn to the people in your group and have at it for a minute and a half. Okay, it's time to wrap this up. So finish up with your conversations. I'm not going to ask for your feedback this time because I think I know exactly what you said without listening to you. That's because I've been in some presentations where I was very familiar with the content that the person was presenting, and I was bored stiff, right? Because what was happening in my brain was this person said something, I said, check, yeah, I understand that. Next point, yep, I understand that. In terms of Piaget's theory, what was I doing? I was assimilating this new information into my existing concepts, my schemas, without changing anything. So I walked out of that presentation no more intelligent than I was when I came in. I was just rehearsing what I already knew. That's not learning. That's not intelligent behavior. But then I've been to presentations where I didn't have a clue. And what happened then in my brain was this new thing, I don't know what that is. Next thing, I don't know where to store that information. It doesn't connect to anything I already know. Next thing, oh, by now it's, why did I come to this talk? Okay. So do you understand the point I'm trying to make is learning occurs best when there is some balance between assimilation and accommodation, where the information is presented to you in such a way that you can connect it to something you already understand. But it's different from what you already understand. It's more advanced. It's a new level in some way, which stretches your schemas, which forces you to accommodate by modifying your schemas to find a place, a way to connect this new information in, and you leave smarter than before because your worldview has expanded. Your schemas are more complex and they're more adaptive to the real world. So that's what happens with learning, according to Piaget. Okay, back to machine learning, though. How are we going to teach a computer to mimic what this 6-month infant is doing? Well, we need feedback, right? Feedback is the key to learning. And when we think about what the child is doing, the child is reaching for that star, and if he or she misses, the eyes tell the child that they missed. That's feedback, right? And about how much they missed. And so then they can try again the next time and they get better and better. The feedback is important for the learning process because the feedback tells you need to adjust the schema to modify it. And so if we think about this formula that I've shown you before about the target position, from now on, I'm going to flip the equation. And we're going to put the target position at the right-hand side of this equation, because I think that's going to make it easier for you to understand that the T is the output value. It's the outcome of this process. And when we talk about neural networks, that's the output is always shown on the right side of the neural network. Okay, so now we're talking about starting with an initial value of X, Y, and Z, and then altering it with some sort of offset value. But in machine learning, we always multiply that rather than add it. Okay, so I'm changing the terminology here. And so we're going to say that the final position T is a function of the initial position X, Y, and Z, each one multiplied by some offset. And in machine learning terminology, we call those weights. And so what it means for a machine to learn means to go through this process again and again and again, each time adjusting the offsets, the weights, in order to get closer and closer to the target. So you need feedback to do that. You have to have some way of knowing that you're getting closer to the target and how you need to change in order to get closer. Now, the early attempts that, already by the late 50s, people were working with feedback loops. They recognized that feedback is important to learning, but they thought that how to solve that problem was to hard code the feedback loops so that, for example, if the target position, if the output didn't quite match the target position, let's say the robot arm went to the right, you could build a feedback loop that says, oh, to the right, then adjust the position by 1/4 inch, try again. If it's still to the right, adjust the position by 1/4 inch, try again. If you went too far and now you're to the left, then adjust the position to add a 1/4 inch. That's built in from the beginning, right? That's hard-coded feedback loop. And it works up to a point, but it's not the final solution. It did allow these machine learning programs to learn from their own mistakes, but it wasn't sufficient. Didn't have the kind of fine grain learning on its own that would be necessary for the next wave of artificial intelligence. And that's where neural networks come in, because neural networks provide a way of feeding information through processing it at each step, allowing us to get closer and closer to the desired outcome. So also, I want to point out again, we've shifted from the mind approach, from trying to emulate the way people do things, to the brain approach, which we don't fully understand, but we know enough about the brain to understand that the brain contains networks of neurons. Individual neurons don't do much, but the networks do. Now, what you see on the right is a typical illustration of a neural network. On the left is an actual network in the brain, much more complicated. But this artificial neural network is usually presented in a way that shows the information flowing from left to right. So on the right, on the left, we have the input. On the right, we have the output. Now, this is intended to represent approximately the functioning of neurons in a neural network in the brain. And so each circle represents a node or an individual neuron in the brain. And each circle, each node has a numerical value, which we can think of as activation level, how excited that particular node is. And then each arrow, notice the arrows are all pointing from left to right. Each arrow connects each of the nodes in one layer, let's say the red layer. Each of those neurons is connected to each of the neurons in the blue layer. And that we can think of that connection as a synapse or a connection between neurons. And each of those synapses has a numerical value called a weight. And so, and when we think about the information moving from left to right, each vertical column represents a layer in the network. So we go input layer, a hidden layer, connection layer, and then an output layer. That would be the simplest form of neural network. Now, I've showed you this photo before. This time, I'm not going to talk about Donald Mackay and Alan Turing. This is the Ratio Club in 1952. I want to talk about the fellow in the yellow circle, Giles Brindley. Now, his claim to fame is his research was on the physiology of the visual system. Now, the retina and especially the visual cortex. And so he's one of the people who identified the fact that the visual system consists of layer after layer after layer of processing, and that each neuron in one layer is connected to many neurons in the next layer. And that the level of excitement reflected by the firing rate of each of the neurons that are connected to the neuron in the next layer, the neuron in the next layer represents it's doing a kind of calculation. It's an analog calculation rather than a digital calculation, but it's still doing some kind of calculation that takes into account sort of the weighted average of the excitement reflected in all of the neurons that are connected to it. Does that make sense? So we got information passing through the human visual system in a way which suddenly people started thinking we could do this with computers. We could approximate this with computers. Okay, now if the audio is turned up, we'll be able to hear a short clip about neural networks.
First, you should understand that an artificial neural network, also called neural network for short, is at its core a mathematical equation. No more, no less. A powerful neural network is typically a very complex equation, but nevertheless, it's just math. The term neural network comes from its analogy to neurons in our body. In our brain, we have around 86 billion neurons. These neurons are what give us the ability to do anything. They send the signals to the various parts of our body to act, and they send signals to our brain that can enable us to think and be humans. Neurons and neural networks serve an analogous role, and that's why the nomenclature is similar. But let me stress this from the start. Neurons in our brain are much more complex and advanced than neurons in an artificial neural network. Artificial neurons do not work the same way. The analogy with artificial neurons is limited because it applies to the way that they are networked, not to the way that they function. Like in the brain, we connect multiple neurons together and form a neural network, which we can train to perform a task. If we continue the analogy a little further and look at a biological neuron and that in an artificial neural network, we see why it makes sense to draw this comparison. A biological neuron has a cell body with a nucleus. This is the core of the neuron where the processing takes place. Around the cell body, there are dendrites, which are signal receivers. They take in inputs, which the cell body can then process. On the other end, there is an axon, which ends with the terminal axons that can pass on a signal to the dendrites of the next neuron. In a similar way, a neuron in a neural network is a processor, which is essentially a function with some parameters. This function takes in inputs, and after processing the inputs, it creates an output, which can be passed along to another neuron. The input is analogous to the dendrites, and the output is analogous to the terminal axons. The function in the neural network is like the cell body. Like neurons in the brain, artificial neurons can also be connected to each other via synapses. This is what a neural network is. It's neurons connected with each other, receiving inputs and passing along outputs in a complex network. While an individual neuron can be simple and might not do anything too impressive, it's the networking that makes them so powerful. And that network is the core of artificial intelligence systems.
Okay. I hope that that was a clarifying rather than confusing video clip for you. Let's go through the terminology 2 more times because I want you to get this stuff. Okay, so remember, each circle in the neural network represents a node, which is a neuron. And each circle has a value, a numeric value representing its activation. Each arrow is a synapse. It's a connection from one neuron to the next. And in the human brain, the connections go both ways, but in neural networks, they always go from the left to the right, okay, from the input to the output. And there are numerical values for each of these connections, which will add weights and something called biases. And each vertical column in this neural network represents a new layer of processing. Okay, one more time, last time, talk about this. Okay, nodes, individual neurons, right? Each node has an activation value, which represents how excited it is. And that activation value is going to influence the next neurons downstream. Nodes are organized in layers, just like the layers in the visual cortex. So every vertical column represents a layer. And so what it's important to remember is that in a typical neural network, every node in the left layer, the red layer, is connected to each individual node in the middle layer, right? And each node in the middle layer is connected to each individual node in the output layer. So these connections are exhaustive in the sense that the value 0.82 up there represents the weighted average of every one of the nodes in the previous level. Okay, now the weighted average, what do I mean by that? That's a numerical value again. Each connection has a weight associated with it, which kind of determines how much influence or importance that particular node in the left layer is going to have on the actual activation value of the corresponding node in the rightmost value, in the rightmost layer. And finally, sometimes it's necessary to shift the value of an entire layer. So layers have associated another value called a bias. This is the last time I'm going to mention bias because it's unnecessarily complicated. If you can get the idea that nodes are connected to other nodes by like a synapse-like connection that has a weight, I'll be happy with that. Okay, here's your chance to ask questions. Does this make sense? Now, information flow from left to right, and the important thing is how highly activated each node is, and that activation value is the result of a weighted average of all of the nodes in the previous layer. Okay, moving on here. Once again, I want you to talk about it to try to drive this point home. I'm not going to ask for your interpretation. This is just your chance to practice. So turn around, get together with the people for one last time here and see if you can explain this to each other. Minute and a half. Okay, it's time to wrap this up again. All right, moving on here. I want to give you a concrete example of how we could build a neural network that could identify the position of a dot that's flashed on a screen. And so in order to make this work, we have to somehow activate the input layer. And so each of the nodes in red there in the input layer is connected to a brightness meter, a luminance meter that's picking up the amount of energy that's falling on a part of the screen. So the top red node is the meters focused on the left half of the screen, the bottom red node focused on the right half of the screen, and the middle node is focused on a band that kind of overlaps the two halves of the screen. And this is to simulate the way the human retina actually works, where we have the left side of the retina and the right side of the retina and kind of a space in the middle where it's connected to both sides of the brain. Okay, so already we can see that the dot of light shining in the left half is activating the top red node more than the bottom ones. The bottom ones are getting kind of ambient illumination, and so they're not zero values. There is light falling on that part of the screen, but not as much as the left side of the screen. So this is processed with, each of the hidden node values. Activation values represents the weighted average of all of the activation values in the red level. And so already we see some intelligence showing up here in that the top two nodes in the hidden layer are beginning to be more highly activated than the bottom ones. And this carries through even more strongly with the next level of processing. So by the time we get to the output layer, it's pretty clear that this system is going to predict that the light fell on the left half of the screen. Does that make sense? Okay, now this example is taken directly from a very famous milestone that happened in 1967, where Frank Rosenblatt, an American computer scientist, finally got his perceptron working. He had been working on it for about 10 years, and it was based on Giles Brindley's description of the layers of the cortex, as well as the work of Hubel and Wiesel. Some of you heard that Hubel and Wiesel won Nobel Prize in the late 60s for their work on analyzing the firing of individual cells in the brain, in the visual cortex. Okay, so he called this machine the perceptron. It took up an entire room, and it only had three layers. It had an input layer, a processing layer, and an output layer. And so that turned out to be a problem in generalizing this, but he finally got it to work so that it could recognize all 26 letters of the alphabet. So imagine in this example, we project the letter X onto the input layer screen, and the individual receptors, the individual meters that are reading the light that's falling on them are being activated in sort of an X pattern. And then they're sending their signals to the intermediate layer. But so each each of the neurons in the intermediate layer is receiving input from all of the neurons in the preceding layer, but each neuron connection has a different weight. And so then the same thing happens as that information is transferred to the output level. So by the time I got to the output level, the system could report this was an X. It worked. The perceptron was the first working example of an artificial neural network all the way back in 1967. Now, this is kind of when I came on the scene. I started graduate school in 1973 when Frank Rosenblatt's work was still exciting to everybody because they couldn't believe that it was possible to do it. And another fellow by the name of Oliver Selfridge had developed a model of how this worked called the pandemonium model. So when that's a pun, intentional pun, because this model is portrayed as each of the layers has nodes, but these nodes are demons, little demons in your head, and their activation level is expressed by shouting. And that's why he called it pandemonium, because you have all these demons, and when they're all shouting, it's pandemonium. It's a chaotic kind of scene. But this models what Frank Rosenblatt's perceptron was doing, right? And so if you follow this through, the first layer is the input layer. And so we project the letter R on the input daemon. And so that the input daemon passes that on to the next layer, the feature detector layer. The feature daemons in the first hidden layer, each one has only one job. One of these is detecting vertical lines. Another daemon is detecting horizontal lines. Another daemon is detecting diagonal lines. Another one is detecting continuous curves, a circle. Another's detecting a half circle, arcs, and that sort of stuff. And so you can see that they're sending their information to the third layer, the cognitive daemons, which each represent a letter. And so the cognitive daemons are watching all of the output of the feature daemons. They're listening to it and trying to figure out if they're being called. And so the feature daemons are saying there's a vertical line here, there's some horizontal lines. And so the D, I don't know if you can see that, but in the upper left-hand corner, there's a D. That D is getting pretty excited because it sort of matches the D. And the P is getting pretty excited, but the one that's screaming louder than any of the rest is the R. And so the output layer, the decision daemon, is listening to this pandemonium and saying, D, P, R, okay. And so the output, the decision is this must be the letter R. That's the pandemonium model. And it all depends on the activation level being passed from one layer to the next layer. Each daemon is evaluating all of the outputs from the previous layer and passing it on to the next layer. Now, this is called forward propagation or forward pass. So when we think about neural networks, we're always moving from left to right. And the value of or activation for each node in one layer is being passed on to the next layer, multiplying the weight times the activation value of that, and then taking the weighted average of all of the nodes in the previous layer to get to that. Then in the output layer, simple decision, the output node that has the highest activation level is the one that will be chosen as the solution, the decision of the process. Now, here we come to probably the most important thing that happened in the 1980s for artificial intelligence was the implementation of a process known as backpropagation. Because this forward pass model worked pretty well, but still required hand tuning. So you get through the process and you discover how much error there was between the desired output and your actual predicted output. And then you tweak the weights by hand to get it to go better and better and better. Why can't the computer do that? Well, the computer doesn't know how to do that because it doesn't have a way of figuring out how much to tweak each of those individual weights. That's where backpropagation comes in. Now, we can't use backpropagation everywhere. We need to be able to know what the answer is. And so this worked ideally initially for recognizing handwritten letters, right? Because we have, let's say we have 1,000 examples of handwritten letters, and we have a human tagging each of those with the actual letter that it represents. So we have this thing on the left, and some human has tagged it as an R. Perfect, right? Now we can run that R, that the handwritten R, through our system forward propagation, and then we see what numerical value is predicted at the end, because each of the letters has a numerical value. The correct answer is a numerical value. How close is our prediction to the actual numerical value of the correct answer? And the difference, that error, we refer to as the loss. How much loss is there? How much error is there at the end? Now, two individuals, I mean, this idea had been floating around in the 1970s, but nobody figured out how to use it. But then David Rumelhart and Geoffrey Hinton, one of my heroes, published a paper in 1986 in which they laid out a way of actually doing back propagation in an artificial neural network. It involves a form of calculus. It involves something that involves the process is called gradient descent. I'm not going to explain it, but if you're interested, Google it. Gradient descent. We'll talk about the calculus involved. The important point is this, for the first time, provided an automated way of taking the amount of error and letting that trickle back through each layer of the network, back propagation, adjusting the weights in each layer as you go through so that the next forward pass, you get a better prediction. And now this assumes we're going to do thousands and thousands and thousands of loops here where we make a prediction and then trickle the error back through and make a prediction, correct the weights, make a prediction, correct the weights a little at a time, and eventually we get really good at doing this. This is Geoffrey Hinton's work. Okay, now we don't have time here. I'm going to skip over that next one because I want to leave a couple minutes at the end for general questions. Okay, so the 1986, here back propagation is added. So 67, we had neural networks. 86, we had back propagation, a way of correcting neural networks, allowing them to learn on their own. It still took another 10 to 15 years before the computer hardware got powerful enough to be able to actually put this into use and allow many. See, the key is not just an input layer, a hidden layer, an output layer, but an input layer and thousands of hidden layers, and then an output layer. That's where you get the real improvements. And you need a very powerful computer with lots of memory capacity to be able to do that. So this is called deep neural networks, been in wide use by the turn of this past century. Okay, so now we are jumping ahead to 2017. Another important development was the use of what's called a transformer model on top of the large language models. This is called deepening the neural network. And so what we now know as ChatGPT and so on have so many hidden layers that no human alive can understand exactly what's going on. This is where it starts to get scary, right? Because in the earlier implementations of AI, humans, understood the programming, so they knew what the computer was doing. But now with this back propagation through thousands and thousands of hidden layers, nobody understands really what's happening. We just have to look at the output and see if it works, just like we don't understand completely how the brain does what it does. We look at the output, and some brains work pretty well, others not so well, and we judge the output rather than trying to understand how it's actually working. Now, why do we call the new forms of AI generative AI? It goes back to Lady Lovelace's objection, right? These systems, many people believe, are creating things that go beyond what the programmers put in. So you have with the programming logic, and then the output exceeds what the programmers told the computer to do. The computer learned on its own to go beyond what the programmers were capable of telling it to do. That's generative AI. Now, these systems are tremendously expensive, require a lot of NVIDIA chips, right? And they also consume tremendous amounts of electricity, enough to power a small city. So one of the things we're going to talk about next week is the impact on the environment of these tremendously powerful and energy inefficient systems. Okay, I want to quickly take you through ChatGPT. Why is it called GPT? It's the chat obviously comes from ELIZA, right? 1966 chatbot. The GPT is generative pre-trained transformer. So ChatGPT is an example of something called a large language model, LLM. And there are many examples now, but this was the one that first came to our attention. The basic way to construct a large language model is to build a neural network and then feed thousands and thousands, millions, billions of pages of text into that model. And what it's doing is looping through each of those text inputs and trying to analyze the relationship among the words and among the paragraphs, among the sentences in that text, and then storing that in a form, a numerical form that humans can't understand, but means something to this large language model. It's a representation of the relationship among all of these words and sentences. And then we put it to work after we've trained it, we've pre-trained it, and now we put it to work predicting words. So if the test sentence is the quick brown blank, we want it to say fox. We want it to predict fox. That's pretty easy. But John blank reading, that's a harder thing because it could be in any one of a number of words, but the most common one is John loves reading or John hates reading. Okay, so now we hire a bunch of low-wage English-speaking people, probably in Kenya or Nigeria or somewhere else, India, and we have them compare the output of our large language model to the expected output and give feedback. So that's part of the training. First, we have the large language model absorb all this text and find the statistical relationships among the words. And now we have it predict things and we give it human feedback. And then now we're ready to accept queries from people to try to draw out some of the information that's in this large language model. And this is where the transformer comes in, because the transformer, the new thing that transformers were able to do is, instead of my 1985 attempt, which treated each word as of equal value, transformers process the whole sentence, the whole query, or the whole paragraph that you put in asking for something, and gives attention to certain words and phrases which are deemed by the transformer to be more important than the rest. And that's how we get such good output, is because these transformers have gotten so good that they can identify what it is that you're asking in that question. What's the most important thing? And then generate an answer that fits with that. So then the pre-trained large language model then gives you back a response which matches the query that you gave it. And then these things still need further training beyond the pre-training, because they keep getting better over time as people give feedback, up or down, thumb up, thumb down. This was a good response, this was a bad response. So I tried this, okay? So a couple weeks ago, I said, generate one paragraph about the history of the Hope Academy of Senior Professionals, HASP, okay? And this is ChatGPT. You can see the symbol on the left. Okay, and it says that HASP was founded in 1993. Wrong, right? And it's based in Hope, Arkansas. Okay, a plausible answer for a large language model. The word is hope. What's the most likely next word? Well, it's not Hope College, it's Hope, Arkansas. And according to the pre-training that this had. Okay, so I said, nope, I did a thumbs down. And I said, and now, first of all, this is good because it picked up history and Hope Academy. If you'd done this, a couple of years ago, you would have gotten all kinds of web pages back about hope and, building hope and about military academies and all sorts of other things. It actually focused on my question and gave me a pretty good answer, but it was wrong. So I said, revise the paragraph so that it applies to HASP in Holland, Michigan. Okay. So first of all, now it's got enough memory that it can keep track of the previous query. And now I can just ask questions about revising that query. I don't have to type it all in again. Now it's better. It says it's in Holland, Michigan, and it was established in 1997. That's still wrong. Okay. So if you look at, there's a web page freely available on the web about the history of HASP. And so you would think that that ChatGPT would be aware of what was in that web page since it scoured everything else. Why didn't it look at that web page? But apparently it didn't. And so then I actually I directed it, revise the paragraph again, this time using historical information from this website. I gave it the website, and now it came back, and now it said it was founded in 1987, which is close because there is 1987 appears in that web page, but it's not the founding date because the founding date is listed as 1988 in that web page. So it picked up part of the information from that web page, but not at all. Okay, we still have a ways to go, right? It's getting pretty good, but you should not rely on the output. If it's important that you get it right, you better check it because there are all kinds of ways that the LLM can come up with information that's plausible, but not accurate. Okay, so I'd like to leave you with this idea. And this feeds into next week. Okay, ChatGPT and all the rest of these have been trained on vast collections of human-created material, art, music, text, books, whatever, web pages created by humans. And the idea of neural networks came from human scientists and engineers, programmers. Therefore, from many points of view, generative AI, as powerful it is, still reflects human intelligence rather than true machine intelligence. And there are philosophers who are still arguing this. I think it's open to debate. Is AI truly intelligent, or is it still reflecting human intelligence? We'll talk more about that next week. Okay, I came right to the end here. Do we have time for any questions, or do we need to leave right now?
We'll take a couple.
Okay, right there.
This isn't a question. It's a comment, though, that with all these advances since over the decades,
Yes.
Will it be less often that I'm speaking with a computer on the phone and they say, I don't understand?
Yes, it will be less often. The speech recognition and speech synthesis is improving year by year still. It's going to get better, but it's never going to be perfect. Just as when my wife tells me something, sometimes I misunderstand her. Okay, I'm not going to get any better, but the computer is going to get better.
These various AI platforms, is there any mechanism where they're connected so what one is learning is shared with the other?
No, they're all, and that's one of the problems, is they're all proprietary. They're run by different companies. Many of the companies are profit generating companies, and they are not about to let anybody else share their technology. And so unfortunately, they are not talking to each other, but there are some kind of overarching frameworks that allow you to use to compare information from several of these large language models. My current favorite is Perplexity, which often gives me information from ChatGPT and other places as well, but they're not sharing the technology. So if one model is trained on this web page, now it'd be interesting to see if you ask ChatGPT to generate a paragraph about HASP, will it be better just as a result of my downvote on the query that it gave me? Maybe it's better by now than it was 2 weeks ago. Okay, one more question.
While you were teaching by asking additional questions about HASP and giving additional data to get a desired outcome, I couldn't help but think about the TV show Star Trek with Kirk in the issue where they had Vega, which was Voyager, that had lost some letters off the side, and now Vega was the intelligent one. It's about to kill Kirk and his ship people. My question is, as these computers get smarter and smarter and smarter, it will require the same kind of thing you did, asking questions to get to the conclusion you want, like Kirk getting out of trouble with Vigo ruling his life and going to kill him. Will it require some kind of supercomputer to ask smart enough logical questions to get the future machine intelligence to a safe answer for humans that we can live with?
That's part of what that New York Times article talks about, working together across the nations, across companies, to try to come up with guardrails about preventing small, we're entering an era of autonomous AI agents that are not only going to be able to give you information, they're connected to real things so that they can order for you. They can do things for you. They can make appointments for you. Are you sure you want you want to turn that over to a computer? Is there anybody checking the output of that, making sure that it's accurate and that it's what you really want before they drain your bank account, right? Oh, so anyway, more on that next week.
Thank you very much. Let's express our appreciation.
Thank you.